but to other scientists as well. These chips are seen in all 4 of these samples, and you see the pictures here from our paper. We did a consistency check, of course, and analyzed the elements present. It's actually a fairly simple structure in this red material, but a very important structure as you look at the chemical signature, which involves iron and oxygen, as well as aluminum and carbon. And notice there, well, I don't know if there's no zinc in evidence. That becomes important in a moment. But this question, perhaps there's a prosaic explanation for these chips. Perhaps it is just paint, and in particular primer paint, which was applied to the World Trade Center steel, which has a red-orange color, similar to the color that we see here. So we finally found a sample of the primer paint. Now, as most of you know, over 99% of the steel in the World Trade Center buildings was quickly shipped to Asia and melted. It was recycled. This evidence from a crime scene was destroyed. Over the objection of many scientists and engineers, now, nevertheless, some of the steel has been preserved in memorials. This particular memorial is at Clarkson University in New York State. The fellow that put the monument together for the university was kind enough to go to the monument and extract some of the paint off the surface. So this is actual primer paint then from the World Trade Center. And what we have is the analysis of the paint on the bottom plot, and for comparison, the analysis, the chemical, the elemental signature for the red chip material on the top plot. And you can see that they are distinctly different. The paint shows a very strong signal of zinc. There is no zinc in the red chip material. There are other differences that you can see. The calcium peak is enormous in the paint, for example. Now, when we look at the red material, this anomalous, now I can call it anomalous because it doesn't behave like paint, certainly very distinct from the primer paint actually used in the World Trade Center. So now we use a scanning electron microscope to get this remarkable image that appears in our paper, showing faceted grains of iron oxide and aluminum in the plates. If you look towards the center of this picture, you can see both plates and these faceted grains. And the gray material, it looks gray actually on this image from the electron microscope, is an organic. And you know, I have people say, well, maybe the building's collapsed and then somehow you just form this nanothermite material. Well, it turns out to be quite a bit more complicated than that because of the very ultra fine, this is at 50,000 power, we can finally see the plate-like structures containing aluminum and the faceted grains that are also very tiny, about 100 nanometers across. This is nanoscale. It's just hard to comprehend how difficult it is to reach that scale. And notice the uniformity, if you can see then, in the faceted iron oxide grains. Anyway, then you've got the organic mix, and my reaction as soon as someone says, well, maybe the buildings just fell, and you know you've got iron oxide, which is rust, I agree, and aluminum in the buildings, and they come together and form nanothermite. My question is, yeah, well, where does all the organic material come from, and how do you get these all formed intimately combined in this mixture, and to get it to react rapidly as it does? In this plot, which is described in more detail in our paper, the blue curve shows the reaction of the red material from the World Trade Center. We did this with from all 4 samples. This is one of the samples. Notice that it goes to a high peak there in watts per gram. The red peak is from known nanothermite. This is from a paper published by Lawrence Livermore National Laboratory, scientist there, which is just down the street, basically, here, not too far away. And this is a 2001 paper, meaning that they had worked on this, of course, for years prior to this. Both of these curves show a very high energy release in short times, and in fact, the red material from the World Trade Center 7 years later, when we did the test, reacts more rapidly than known nanothermite. It's a very remarkable stuff. In the words of my colleague, Dr. Fair, it blows up. And this is from the World Trade Center dust. Still blows up. Following the tests, these ignition tests in the DSC, we looked at the residue and we observed numerous iron-rich spheres, which Richard talked about, so prevalent in the dust. Now, these spheres were not present in the red material prior to ignition, but following ignition, they are present. This means, it doesn't just suggest, it means that there were very high temperatures present. And furthermore, we find iron oxide beforehand. I'll show you data on that in a moment. And we find elemental iron, that is, not enough oxygen to produce iron oxide after ignition. That means the iron is reduced in chemical terms, which means there was a thermite reaction. No other way to reduce the iron and produce these spheres from this material as we have observed and published in a peer-reviewed paper. Now here's some new data. Here are some new data. Transmission electron microscope data showing in the circle one of our iron oxide grains. The scale here is 100 nanometers, lower left-hand corner. So these are indeed very ultra-fine grains. We then look at the TEM electron diffraction pattern for this grain that was circled, and we see a very clear diffraction pattern, the bright points that you see here. By analyzing the lattice structure that is denoted by this electron diffraction pattern, comparing with known elements. So here in this table, Dr. Fair is comparing the d-spacing in angstroms, second column, with the d-spacing in angstroms of iron oxide, Fe2O3. And we find a match, an exact match, showing that Fe2O3 is indeed a component of this red material from the World Trade Center dust, and these ultrafine grains. And by the way, no elemental iron was found. It is present after the reaction. That's what you expect from the thermitic reaction, the production of iron from iron oxide. What happens is that the oxygen associated with the iron oxide transfers over, is taken by the aluminum so that you form elemental iron. It's very a vigorous reaction, of course. My last slide. This is our paper. Dr. Niels Harrit is first author, and he's doing a wonderful job of spreading the information about this science. This is a peer-reviewed paper in an established scientific journal. I want to emphasize that this paper has not yet been challenged in the literature, the peer-reviewed literature. In the protocol of science, the established protocol, we have published our findings. It took months to get this through peer review, I might say, but it has been published. And as David Griffin pointed out, it's receiving a great deal of attention in Europe. We're hoping, beginning with this conference, we'll get some attention in the media in the United States. Thank you.
Coming up in the next segment of this historic press conference, our special guest, citizen, activist, firefighter, and founder of Firefighters for 9/11 Truth, Eric Lawyer.